let's say we have an original data set right here. This is our original that maybe goes between about 2.5 and 6 or so. And one of the things that we want to do is scale this over to some normalized values, maybe scale it between 0 and 1, or we scale it the mean to 0 and have a standard deviation of 1. So I'm going to just give you a formula first, and we'll jump into the code on how to do this. Any standard scalar of most types of scalars, we're going to use the form y equals and then a times x minus b. All right, and each scalar is going to have a different a and a different b. Now, two popular scalars that we're going to work with are called a standard scalar, where we divide by the standard deviation. So that means that the a value equals 1 divided by the standard deviation, sigma. And then b is going to be equal to the mean value, x. So this is our scaled output, and this is our unscaled input. Okay, so that would be like the blue. Over here, this is our x value, and then our y value is going to be over here. Now let's also do a min-max scalar. So if you have a min-max scalar, the a value is going to be equal to 1 divided by x max minus x min. All right, and then the b value is going to be equal to x min. So those are the two scalars that we're going to be using, and you'll see this is going to be the green. This is the min-max right here. Min-max scalar with 0 to 1. And then this orange right here, we call that the standard scalar. Okay, so what we want to do now is go ahead and just try some of this out in Python. And we're going to first of all just create these distributions with some data. So I'll just go ahead and import Numpy and matplotlib, and then we'll generate a distribution of data. So I'll just create some random values. This is going to be normally distributed values between, this is going to be this blue right over here. I'll just show this to you right here. Okay, there are our blue values that we're going to generate with this random number generator. Okay, and then let's go ahead and just do a standard scalar. That's going to be the very first one, which is the mean 0, standard deviation 1. And we can see that here, x minus x mean. Okay, the NumPy mean, and then divided by the NumPy standard deviation. Another one is going to be the min-max scalar from 0 to 1. So here we have z equals, and then we do x minus the minimum, and then divided by the NumPy max minus the NumPy min. Okay, so we're going to plot the distributions as histograms and show it. And I'll go ahead and just run this one to show that we've regenerated that figure that we had previously. Now let's go through a couple different exercises together. This is how we do the scaling in NumPy, but there's a really nice package in scikit-learn that helps us with that, so we don't have to do each column individually. And we can also there's some additional options as well on those scalars. So let's go ahead and just start with, after this distribution, let's go ahead and just import the sklearn, and we need to also just do a train test split. And that'll actually be shown in the next module on train test splitting and for splitting the data. But let's just go ahead and do this just so we can have our separate data sets. We're going to import train test split. And then we'll also import pandas as PD, just so we can import the data. And then I'll get the data. This is going to be from a URL, just to import the data. And this one's going to be this web address. Alright, it's a little bit long, but there it is, TCLab data6.txt. Alright, and then we're going to do read CSV, and this will be the URL. Alright, let's just look at the data. Okay, so after it imports, it's going to show the data head with 5 columns. Now, let's go ahead and just set the index as our time. And so I'm going to do set index as time, and then let's just do in place equals true. And let's get our head again, just be able to see it. Here is our data that has the time as the index, just so for plotting and other things it looks a little bit better. Okay, now we're going to do a train test split. And so I'll do my train and test are going to be this train test split. And again, you'll learn this one in the next module, but we're just going to divide it up so that the test size equals 0.2. And then I'll just say that shuffle equals false, just because it's time series data. Okay, that just gives us our train and test data sets, and you can see those are just the first 5 of that one, and then if I go to test, you can see the different times. It starts 80% of the way in for the last 20% of the data. Okay, now what we want to do is do our scaler, and this one's going to be the Sklearn pre-processing package. So I'll do Sklearn and pre-processing, and we'll import the standard scaler. Now this is the one that divides by the standard deviation and subtracts the mean value. And so I'm just going to create S, that's going to be my standard scaler. And then I'm going to use the fit transform. And let's just print strain now. Oh, I need to put in my data. This is going to be my training data. Okay, and you can see it returns it as a Numpy array. But let's just take a look at the scaling factors here. And so if I do s dot, and then this one is scale underscore, it shows me the scaling by the standard deviation of each of the columns. Alright, and I can also look at, instead of scale, I can look at the mean value as well. So it shifted it over by the mean, and then had that standard deviation. Now if all the values are 0, you can see here it's just going to use a value of 1 for the standard deviation. So it doesn't want to divide by 0, so if it is a very small number, there's going to be a tolerance there to say, well, don't divide by that small of a number, just put 1 there instead. Okay, so this is scaled with the standard scaler. Now we can also do the test as well. Okay, the scaled test data. And I'll just put in the test. Alright, and then you can also see that data, just printing this out. Okay, so these are scaled as well, but one of the things that's really important is if you're going to be doing the training, you don't want to necessarily do a fit transform on the test as well. You just want to do a transform to use the same scaling values as the training data. Okay, because if you have different scalars, when you go to validate your model, you're going to have a different range of values. So you actually want to do a transform there instead of the fit transform. Okay, if you want to apply the same scaling values as before. Okay, so what I'll need to do first of all is go ahead and just do the fit transform on the training. Okay, to be able to get our standard scalar, we're going to fit and adjust the standard deviation and the mean value based on the training data, and then we're going to use that same standard deviation here on the test set, and that'll change the answer just a little bit. Okay, so let's go on to the next one if we want to convert this back into a data frame. These are nice as NumPy arrays, but it's much more convenient to work with it as a data frame. Let's just come down here and shift enter to create a new cell. And so I'm going to have a training data frame that's going to be pandas and then call it data frame. And I'll put in my NumPy array, and my columns are going to be equal to my original training columns. And I'll just put values there. Okay, so if that's strain data frame, I'll just look at the head for that, so I can see that I now have scaled values in here instead of the unscaled. And if we do the same thing for our, let's do the same thing for our test set. And I'll just copy this one and change it to test. Alright, and the data column names are going to be the same here, but I'll just go ahead and put them in. Okay, and then we can look at the values. Okay, so here's this is going to be our test set we're going to use for validation. Okay, let's go ahead and just enter a new cell. Now what we want to do is do a Minmax Scaler as well. So this one is going to be from the Sklearn Minmax Scaler. It's also in the pre-processing package. So from Sklearn pre-processing, we'll import Minmax Scaler. And then similar to the last one, we're going to create that new variable s. And here we can adjust the feature range. So in this case, I'm going to do 0 to 1. But another common one is -1 to 1. And then I'm going to have my training data. And this is going to be fit transform. Okay, and then my test is going to be just transform. Okay, and then let's just look at some of the results of that. I'm going to have S, and then this is going to be our scale. Okay, this is how 1 divided by the difference between the max and the min. And then let's also look at, instead of scale, we're going to do min. So before we had, if we come up here, the other one was scale and then the mean. Okay, so for the other one it was scale and mean for the standard scaler, and then the intercept value, the one that we subtract, is going to be the min on this one, not the mean. So let's just look at that one. Okay, so there's the min value for each one. Okay, let's go down. We're going to convert, if we ever want to convert, again, these back to a data frame, then we do something similar with this, just like we did on the last one. We just convert them back into data frame values. Okay, there's the training, and we also had our test as well. Okay, this is just going to show the last one, that's the test data frame. Okay, let's continue on. We're going to now just show how to do the inverse transform. So if you're in the scaled area and you want to be able to transform it back so that you can look at results in the original units, you can do that just with the inverse transform function. And so let's do that for our test, and then print out the x value. Oh, I forgot the s here. Transform. So you can see it did the transform back to the original scale. All right, let's go on to another one. We're going to do an exercise, and this is going to be the temperature control lab has 2 heaters and 2 temperature sensors. Heater 1 is cycled between 0 and 100%, and heater 2 is off. Okay, we're going to have a histogram plot first to show the heaters and the temperature distribution. So we had our URL from before, and we want to use this data to be able to import and visualize what's happening with this. Okay, so our data is going to be read CSV. I'll just import this again so we can have it, and then I'll do the set index again. And in place equals true. And then let's do data plot, and we'll do kind equals histogram. Okay, but it doesn't really show the granularity that we want. So let's change a couple options on this. Maybe the bins equals 30. Okay, shows it a little bit better. Let's also do another thing. We're going to make this figure size just a bit bigger. All right, not too much bigger, but then also let's put an alpha value so that we can see the things underneath it. Okay, so we can see some of the green distribution here. We can also see the Q2, and then also some of the Q1 there as well. So that one is between 0 and 100%. Okay, for the Q1, and then here is temperature 2 and temperature 1. So we can see all those distributions. We want to scale those, and first of all scale them with the standard scaler, and then we'll plot the new distributions. Okay, so for this one, just generate a new cell below, and let's go ahead and do the S equals the standard scaler, and then we'll have our S data equals, and we'll do fit transform with our data. Then S data equals, and we'll convert this back into the data frame. And this will be S data. We just really need to get the column names. So columns equals data columns dot values. And then let's make our index equal to data dot index. Okay, just preserve that time as the index. Okay, let's just look at that data, the scaled data. Okay, so here's our scaled data with the times, Q1, Q2, T1, and T2. And then just create a cell below it. Now let's go ahead and just plot it as well. So we plotted the original unscaled. Now we want to be able to plot the scaled data. This is going to be a histogram. I'll do my alpha, especially important here because they're going to be overlapping. and I'll just do bins equals 10 on this one instead of 30, and let's increase the figure size. Let's see, we could do 10 by 5 for this one. Okay, maybe we wanted, let's do 30 bins instead. Alright, so here we can see the distributions now. Everything has a standard deviation of 1 and also the mean centered at 0. Okay, so let's go on to our next one. Okay, so what we want to do now is train a neural network to predict T2 from Q1 and T1. Those will be our input features, and we'll split the data into a train 80% and test 20% set. We'll create a parity plot of the predicted versus the measured T2. So for this one, we're going to import Sklearn neural network, and we'll import the MLP regressor. And then we'll also need the train test split. I think we already had that one from before. So if you need to, you can import it again. If you're just running through this exercise and didn't do some of the other ones up above, I'll just go ahead and put that in here. Import, and then train test split. And then we'd also need matplotlib for this one. Plot the results. Okay, let's go ahead and just do the train test split. I'm going to have my train and test values, and we'll do our scaled data with a test size of 0.2, and let's do shuffle equals true for this one. Okay, we're going to mix up the data, take it from different regions to be able to split it up. Okay, so for the training, it's going to be equal to, I'll copy this, and then test, let's also copy that as well. I'm going to perform the regression now. This is going to be the neural network with hidden layer sizes equals, and I'll just do 3 and 3. And I'll have my activation equals the hyperbolic tangent, and then let's have the solver equals the BFGS solver, and then the max iterations. Sometimes you need to increase this. I think the default is something like 200, which is generally insufficient. Okay, so there's the max iterations. And now we'll create our model predictions. This is going to be my train, and I just want to use the Q1 and the T1 to be able to predict the T2. And then let's have my labels. That's going to be my T2. Okay, there's my model, and I'll go ahead and just create that. Let's see what my error is here. Okay, it's LBFGS instead of BFGS. So let me come back up to solver. It's a limited memory version of the BFGS solver. Okay, so here I have my model with my neural network. Okay, now let's go ahead and just test the neural network. We're going to create some predictions, and we had test copy. Okay, it's going to be predict. Okay, so I'll just copy that, and then I'm going to add to it. I'm going to add to it just the T2. Okay, this is going to be the T2 predict, and I'll have the test set. And similar to last time, I'm just going to select the features that I want, Q1 and T1. Okay, and then I need to unscale the data just so I can see it in the original units that I had it before. So D1, I'll just say that's S.A inverse transform, and that'll be my test. And then D2 is going to be also the inverse transform, and that's going to be of my predict. Alright, and then I have my test results are going to be my new data frame. And in that, I'm going to add T2. And that's going to be D1. And I'll use the very last column of that. Alright, and then I also want T2 predicted. And I'll do D2. And let me just get the last column of D2 as well. Okay, so there are my test results, and if I run this, let's see, I've got an error here. Okay, Numpy has no attribute predict. Okay, so let's see, what do I need to do here? Oh, I need to, instead of np.predict, it was my neural network predict. Okay, so there it is. Okay, so I'm using my neural network to predict, not Numpy to predict. Alright, and then now we want to just plot the results. I'll just do test results, and I'll plot, and we'll say x equals T2, and then y equals T2P, and I'll make this a scatter plot. Okay, so here's my prediction, just showing the T2. This is going to be the measured value down here, and then the predicted value up here. But let's also just include what a perfect prediction would look like. So that's going to be, I'll add to the plot, and this one's going to be 15 to 28, and then let's do 15, 28 as well. Just create a diagonal. And let's make that a red line. Okay, so this would be a perfect prediction. Right here you can see some of those did not predict very well. Others, you can generally see a cluster right around that line. Okay, so let's go ahead and just do the same thing but with unscaled data now, and just see how it works if we did not scale the data for the neural network. Let's use the neural network but not scale the data and just see the difference in the result with the scaled versus unscaled. So I'm just going to do something similar to what we had done before. We'll import the MLP regressor, import train test split, matplotlib, pandas, and then we're going to read that CSV again, and we'll just set again the time index, split into the training and test sets, just same as we had done before, and also copy some of those, okay, before we create the neural network. We're going to create the same structure, okay, but the one difference here is that when we did the train test split, instead of scaled data right here, this one is going to be just the original data. Now we're going to test the neural network. We'll just add that column, T2P. Alright, and then we'll plot the results. I'll go ahead and do a test plot with T2 and T2P. That's going to be the scatter plot. And we'll add that red line again and show it. Let's go ahead and just run this one and show that the neural network now did not do very well at predicting that. So this is with unscaled data, and then if we come back up, this is with the scaled data. Now, part of the reason for that is that neural networks, they typically have activation functions that are something like rectified linear unit or hyperbolic tangent or sigmoid. And just to show you what those look like, the hyperbolic tangent is going to have an activation somewhere around 0, where it comes up to a value of 1. So right in this region is where you want most of the data. If you have something way out here, like at 50, then we call that like a vanishing gradient. It doesn't really have any kind of slope to the line, so it isn't able to predict anything. And that's why we're getting this very flat surface here on the prediction, is because it's the input to that function is not scaled. And so it's not in that region that's curved on the hyperbolic tangent. Now we could change this. You know, for example, instead of the activation function equals hyperbolic tangent, we could have rectified linear unit. Okay, but you're going to see similar results there as well. And part of that is because the rectified linear unit is going to look like this, where it comes on at a value of 0. So that's where it starts. And again, if you have all of the data way over here, then it really never has that transition point between the two. And so you've really got to have your data scaled so that it goes to that transition point where the machine learning can really be effective. Okay, so that concludes this. I'm just going to show, let's come back to the machine learning course. And I'll just give you the preview of what we've just covered and where we're going next. So let me, oh, not now. And let me just increase the size here. And so here's the overview of the course. We talked about collecting data in our data engineering. We talked about consolidating or gathering data, visualizing some of the summary statistics, feature engineering. We did outlier detection and filters with the data cleansing, and then standard scaler, Minmax Scaler for the scaled data. So that's the, we're going to go on to splitting data after this. This is going to be our next one. And then on to some of these other topics later after data engineering. If you come here to the website, you'll see the scaled data. You'll see some notebooks here. This is in GitHub and then also Google Colab, so you can run these scripts here. And then also a discussion of each one with the source code that we covered today.